In this video, we're going to talk about the shell formula for revolution about a vertical line. The shell formula is a method of slicing with cylinders. And if you create like a cylinder or a cookie cutter slice that might be hollow in the middle, right? Thinking about that cookie cutter slice, something like this, we've cut a cylinder out, right? So here's my three-dimensional figure. And if I slice that right there and I lay it out flat, essentially I'm going to have a long three-dimensional rectangle, right? And if we wanted to find the area of that rectangle, well, the area would be the circumference, 2 pi r, times the height. That's going to give us the area of this cylindrical slab that we've cut out and laid flat. And of course, that volume, we're looking at these as being infinitely small. So even though I've drawn in this slab or this kind of this height here on this three-dimensional figure, that's so thin it's not considered, right? So we've got all these different rectangles, and essentially that's what we're doing, right? We've got base times height, and the base is this circumference that gives us this length. All right, so let's talk about using this formula and what this formula means. So we can find the volume by integrating area, and I just drew you a picture and kind of illustrated how we've developed this formula from an area of a rectangle. So the volume of a solid is generated by revolving the region between the x-axis and the graph of a continuous function. Here we say that this function f of x has to be greater than or equal to 0, positive. And we're going to rotate it about a vertical line. So that line, my bounds, both have to be bigger than that line, greater than. So the integral for volume, or the integral that gives us volume, we're going to integrate area. And as I just said, this is kind of the length, and that's the height. Whenever we think about measuring or determining, what we are dealing with here, thinking about some curve, the radius is always going to be measured out from the axis of rotation. And then the height is going to be measured up from that x-axis, right? We have x, this is my x-axis. So the height is always perpendicular to the variable of integration, and then that radius is going to come out. The radius comes out from whatever you are rotating about. And that's always going to be the setup. And so we could change this, and we could have a formula, volume equals c to d, 2 pi, and we would have a shell radius and a shell height. And those would need to be in terms of y. So if we were taking some graph and say rotating it about the x-axis, my height would come out this way and my radius would measure up. All right? So let's do an example with this problem. I hope that kind of makes sense what I've described there. So for this example, we're going to find the volume of a solid of a region, which is bounded by this curve, y equals the square root of x, and then also the x-axis and the vertical line, x equals 4. Those are bounds. We're going to revolve this region about the y-axis to generate a solid. So let's think about what this picture looks like. I'm going to pull an image in. So let's look at what we have. Here's my curve. Y equals the square root of x. And we want to rotate this about the y-axis. So we have another bound, the x-axis, and the vertical line, x equals 4. Those were all given. So my interval of integration is going to go from 0 to 4. My height comes up. It's always parallel to the axis of rotation. So my height is going to be the function. This curve represents my height. So my height would be square root of x, and my radius varies because if we look at in here, we'd have a short radius, and then looking all the way out there, we'd have a longer radius. So my radius is unknown, it varies. We're going to refer to that as x, and the radius is always perpendicular to your axis of rotation. And it is a lot to remember, and especially when we start to compare this to our disk method, we see that there are some differences. So it's really important that you practice well enough so that you really know what you're doing when you're choosing between these two formulas, because there are definitely times where the washer is easier than the disk and vice versa. So let's look at what this shape or this region is going to look like, or what this shell is that we're cutting out. So here's a slightly more three-dimensional figure. We still have that same curve, and essentially what we're going to do are create all of these cylinders, all of these different cylinders. And if I look at creating maybe a cylinder in here, you'd see it would be much shorter. That height would be different, and also the radius would be different, right? If I had some cylinder cut out in there. And likewise, if I did it at x equals 4, we'd have a much larger cylinder. So essentially, when we are using the shell method, we're just finding the area of all these different rectangles and summing them up, because that's what an integral is. It's the sum of the area of all these rectangles. All right? So you can see in here, it's still the same. That shell height is variable. It changes. My height is going to be the function. And my radius, which also varies, is going to be x. So let's set this up and calculate. So what we want to remember is that volume is the integral from a to b of 2 pi r, the shell radius, which gives me my circumference, times the shell height. And we just defined what that was going to be looking at our picture. So this is going to be my volume is the integral from 0 to 4, 2 pi. My radius is x, and my height is square root of x. So at this point, this is very, very easy for us to integrate. I'll pull my 2 pi out. The integral from 0 to 4, if I multiply x times the square root of x, that is x to the 3/2 dx. So this becomes 2 pi, adding 1 to 3/2 is 5/2, so I have 2/5 x to the 5/2, and we'll need to evaluate that from 4 to 0. So I'll pull that 2/5 out. I have 4 pi over 5, and we have 4 to the 5/2 minus 0 to the 5/2, which is going to be 0. The square root of 4 is 2. 2 to the 5th is 32, and 32 times 4 is 128. So my answer here is 128 pi over 5. That is the volume. And so the volume of what we are finding here looks roughly like this. It's a circle. Okay? So it's a cylindrical shape with a concave, or is that convex? I'm not sure, but we've got this cone kind of carved out of it. And that's the area of that region. So in the next video, I'm going to do this with the same curve, but we're going to go about the x-axis instead of the y-axis.